Now, whenever we have a new quantum mechanical result like this, one of the first things that we want to do is, of course, to check the classical limit to make sure we can explain the behavior that we are already familiar with from the classical world. So I'd like to consider the classical limit of this result. Now, there are two ways to go about the classical limit. So the simple version is to simply ask what happens as h bar goes to 0. What would happen if I turned off quantum mechanics? Well, if I were to do that, and if I look at this energy and this radius that I'm computing, you'll notice the radius as h bar goes to 0 would just vanish. So the radius for my atom would then go to 0, which makes sense because we know classically, right, the electron will eventually give up any energy that it has, and it's going to spiral inward to the nucleus and then sit directly on top of it to minimize the energy, right? So that minimizes the energy E, so that makes sense. We also find that the energy is going to have an interesting value. As h bar goes to 0, this then would go to infinity, so my energy would be heading towards negative infinity. So R goes to 0, it does that, and it minimizes the energy very nicely. And as it does that, though, the energy goes to minus infinity because what's happening is the electron is going to sit right on the nucleus. And, of course, the nucleus then is an attractive 1 over r Coulomb potential, and it's going to give me negative infinite energy. Well, that's good, and that's kind of consoling, but there's more subtle ways to go about this. And this is where things get really interesting because, after all, remember, turning down h bar turns off the effects of quantum mechanics. So I want to consider a different type of a situation. Suppose I had an electron in an orbit of a given radius r, and I simply ask, well, what will happen if I let this electron move around at this fixed radius r from the proton, and then while it's doing that, right, I just turn off quantum mechanics. So this is a little bit of a different limit. I want to take h goes to 0 with r held equal to a constant. Now, at first that might seem tricky, but notice how we can do that. The radius, I want you to notice, right, is determined simply by n times h quantity squared. So if I want to be very explicit about that, that's n h bar squared divided by the mass times the Coulomb parts is the expression that we had up above here. I've simply combined the n and the h into a single factor. And let me rewrite it. It didn't come out so nicely, right? So if I want to keep that radius constant, the way I do it is as h goes to 0, right, I'm going to define n to be proportional to 1 over h. I'm going to keep n times h constant. Or in other words, n will be some constant divided by h bar, and that quantum number n then will be tending towards infinity at just the right rate so that this product stays constant as h bar goes to 0. And that will then allow me to think about this orbit as an orbit involving some very large quantum number. And then the question is whether or not this type of a situation with this kind of interesting limit where n is heading to infinity, h is going to 0, but their product stays constant in such a way that I just maintain a simple orbit while I slowly switch off my quantum mechanics. And the question is, as I do that, can I recover all of the classical physics behavior of this atom? Now, let's think then what behaviors it is we have to account for. Well, you will recall that when an electron, a classical electron, at a given radius from the center of an atom, as it orbits around the atom, it begins to emit electromagnetic radiation within classical physics. So this orbit actually is going to slowly spiral inwards. and lose energy. And as it's spiraling inwards, it's going to be emitting out that energy in the form of electromagnetic radiation. And the question is then, well, one question is, well, what frequency radiation are we expecting to come out? And as I hope you know, that frequency corresponds to the orbital frequency of the electron. So that frequency will actually be equal to 1 over the time, and that's the time for one classical orbit. So we have this classical picture. And what we will pick up next time is whether or not that classical picture can correspond to the quantum mechanics, so that somehow this classical picture of what's going on must be buried into this formula, and we want to tease out exactly how this formula for discrete energy levels somehow captures this interesting spiraling in behavior with emitting classical radiation at a given frequency. And that's what we will take up next time.